To explore chemical reactions, we'd like to know just what's happening to the very smallest indivisible particle in the reaction. Our objective is to find the mass of atoms, and we can come close to it by using a method of comparing the mass of molecules. The scientist Avogadro proposed that under the same conditions of temperature and pressure, two equal volumes of gas molecules contain the same number of molecules. By comparing the mass of the two volumes, we are also comparing the mass of two individual molecules, their relative molecular mass. Relative masses are ratios, and we can apply any unit of mass to a ratio like this: grams, kilograms, or tons. Or we can make good use of the ratio with no unit at all. When working with many values without units, all related to each other, it's helpful to fix one number as the standard. For example, take the number 100. We fixed it as the standard value of $1 because it is exactly 100 times greater than our smallest unit of money, the cent. Every other unit of money has a fixed value compared to the dollar. Chemists needed a standard of relative molecular mass. For many years, they used the oxygen molecule because it combined readily with other substances. It was given a value of 32, 16 times greater than the lightest known gas, hydrogen. The relative molecular mass of many gas molecules can be calculated and compared to the oxygen standard. But aren't we forgetting the original objective, relative atomic mass? Not at all. Using Avogadro's hypothesis to balance gas reactions, we can determine that many gas molecules are made up of just two atoms. So simple division by two gives us relative atomic mass. In this way, we can build up the table of relative atomic mass. Oxygen, the long-time standard, has an atomic mass of 16. Fixing the standard mass at this particular number makes sense when we compare it to the lightest known atom, hydrogen. So we have at last found a way of finding the mass of atoms. But not all atoms. What about all the many different substances which, under normal conditions, are not gases? Over the years, scientists have developed techniques for changing the state of many of them. Some can be heated and turned into a gas. While other non-gases, like carbon, can react chemically to form a gas. But today, it is no longer necessary to gasify substances to measure relative mass. A completely different, highly accurate process can find the relative mass of any kind of atom. It is a process we can compare to highway driving. suddenly a strong crosswind pushes your car. If you don't fight the wind, how far will you get before you crash into the wall? Well, it depends on your speed. It also depends on the mass of your car. A massive car will travel a long way. A subcompact, however, traveling at the same speed, will be blown to one side before traveling as far. By testing several vehicles at a fixed speed, we have a way of relating mass to distance. There is an instrument called the mass spectrometer. It uses a magnetic field, which we can think of as a kind of magnetic wind that blows atoms off their track. The more massive the atoms, the further they travel before they hit the collector plate. Scientists have used the distance between crashes to build a scale of relative atomic mass for every known kind of atom. The mass spectrometer is so accurate that we can measure relative atomic mass with an accuracy to several decimal places. It also reveals another fascinating fact. Let's go back to our cars for a moment. Most of you know that different models come with different options, like mag wheels. These can affect the mass, and so the distance a vehicle travels in our crash tests. It seems as if atoms come with options as well. The mass spectrometer shows that one kind of atom can have several different relative masses. We call these isotopes of an atom. Today, the standard atomic mass has been shifted from oxygen to one of the carbon isotopes. Its value has been fixed at 12, and we call this isotope carbon-12. So whenever we consider the relative mass of any isotope of any atom, the number means its relative atomic mass compared to carbon-12. On tables of atoms, the relative atomic mass is found in the upper part of the box describing each atom. We've followed in the footsteps of chemists who have used the mass of gas volumes and more recently the mass spectrometer to find the relative mass of all known atoms. Now, how can we use this information to help us understand chemical reactions?